right, good morning, everyone. We stopped at number 3, where we separate the variables in terms of v and in terms of t. Let me just recap this problem. I know we finished it, but let me just recap the steps, and then we can move on to the rest of worksheet 1. And we talked about how not all of our differential equations are going to be in terms of x and y. So understanding how things will work out in terms of the variables presented, it'll always be time, t, and something else. Right? If it's not x and y, it'll be t and something else. T is kind of like our x. V is kind of like our y. We separate the variables by cross product. Well, at least cross product will get the dv and dt in their right locations. Once they are there, then either divide or leave it if the variables are already separated. Here in this case, the v is out of place, so we move the v, but the 16 comes along with it. But there's no need to move the coefficients. We only want the bare minimal on the left side. So once we have that, we can identify our u value to be v plus 16. We go through this process, ends up being a natural log problem, or a natural log antiderivative. And the right side, just the power rule, negative 2t plus c. So we've earned most of the points here, getting to this general equation. And the rest is just cleaning up, deciding how we want to solve for c or when to solve for c. And we know there's natural log involved, so typically I like to wait until the end to solve for c, because my equation is going to be a lot cleaner at the end, with c just cleaning up a lot of things for us. So raise e. Okay. Okay, so raise both sides, base e. We get the absolute value of v plus 16. The right side becomes e to the negative 2t times e to the c. E to the c is just the constant. We can make that substitution. We can drop the absolute value. Plus or minus shows up on the right side. And then we can drop the plus or minus because it gets absorbed in by that c. And once we have our general equation, now it's a lot cleaner for me to work in my order pair. So now I can put 0 in for t, negative 50 in for v. And that's going to clean all this up to just give me a c value of negative 34. And I'm able to make my substitution where I initially started plugging in my order pair. Okay, so make sure that you're putting in your c value where you made that substitution and not anywhere else, right? If you put in any other c value, it's not going to be matching. Okay, so that's where we ended on yesterday. We're going to skip b and c involving the infinity and solving for the speed velocity. It's not hard, but just figure that for this test, I'm just going to narrow the focus of what I want us to work on. Okay, so we're going to jump to 4 through 7. I'll put this on a separate sheet, make it easier to read and follow along. Okay, so it says evaluate the integral of x squared over square root of 1 minus x to the 6. All right, so as I look at this problem, I want to go down my checklist. I'm always looking at the denominator to see how many terms there are. All right, there's more than one term, so I know that I can't split this up. It's kind of stuck the way with the form that it's in. So we know expansion is out, separating the denominator is out. Second option is use substitution. The only u value that I can think of is that 1 minus x to the 6. But what's not ideal about that u value?
The x to the 6, it has like a degree higher than the numerator.
Right. Ideally, we want that numerator to be a little bit higher in degree, like x to the 5th, right? So that we can get that to work out. So usually u substitution is going to be best if your u value has a degree that is higher than the numerator, but only by 1 degree, right? There's a big gap there, x squared to x to the 6th. So we're not going to get that u substitution to work out the way that we would like. Okay, so next option is long division or synthetic division, and we know that only works with rational functions and also works if the numerator is the same degree, if not higher, right? We need the numerator to show a much higher degree. It can't be lower than the denominator, so that option is out. And now our last option is arc trig, and with arc trig, the condition is that we do want the denominator to be a higher degree and a degree that is significant. So we need the denominator degree to be higher than the numerator by at least 2 or more. So here we're not going to pay attention to the square root. Just look at the x to the 6th. This is separated by 4 degrees. So that's a potential. It meets that criteria of being at least 2 or more than the numerator. So let's explore arc trig. Okay. So these formulas will be on your formula sheet. But we know by looking at this form, choosing between arcsine, arctangent, and arcsecant, we know at least one is not going to be it, right? We know it can't be arctangent because we see a square root. And now we got to decide between arcsine and arcsecant. Okay, and I think the easiest way to tell is looking at that first term. Looking at the first term, which will be positive, looking to see whether that is associated with the a value or with the u value. And I see a constant there, so that must be associated with the what? With the a value. And with arcsine, one is going to be a, and the other is arcsecant is going to be u. So we see that the constant comes first, the a comes first, so that's going to tell us arcsine will be the better fit for our problem. Our a value is the positive, our variable is the negative, versus our secant, where our variable is the positive portion and the constant is the negative portion. So we know that we're targeting arcsine. Now that we have a goal in mind, we know we have to work with that denominator, right? We need to pull the a and the u value correctly. So the best way to do that, I think, is to get that denominator to show parentheses squared. Okay, I want to have that form gives me the structure that I need so that I can find the a and u value correctly. Okay, so now we're going to ask ourselves, what can I put inside the first parentheses where if I square it, I still get 1? Okay, still 1, right? No changes. Right? 1 squared is still 1. So, but at least we went through that exercise there. Okay, what can I put inside the second parentheses where if I square it, I end up with x to the 6th power? X cubed, right? Let's double check. We know that if exponents are next to each other with no bases separating them, we know we're multiplying it. Right? So 3 times 2 is 6. So that matches, right? So if you can go through this process, you'll ensure that you'll pick the correct a and u value every time. Okay, so let's identify our a and u value from here. Just what's inside the parentheses. You know your a must be a constant. Your u must have a variable in it. And that x cubed is a good sign, right? Because we know that once you get to the derivative, it'll produce something that's x squared, and that x squared will match up nicely, and we should get that x squared to go away. Okay, cross multiply. So now, step by step, I'm going to replace all of my parentheses in terms of a and u, my dx in terms of du, and hopefully the x squared goes away. And we want our rule, our problem to match exactly with the rule. And once it matches the rule, we know we're ready to take the antiderivative. We're now ready to follow the rule. Okay. So x squared stays initially. Denominator becomes square root of a squared minus u squared. Dx gets replaced with du over 3x squared. Okay. Just like what we suspected, the x squared goes away nicely, but keep track of the what? 1/3. Yeah. Now, once that 1/3 comes out, it should match perfectly with the rule that we want to use. Let's double check. Yeah, once we get past that 1/3, everything matches. So we know we can jump into the rule, but careful, before you apply the rule, make sure that you include any coefficient that's part of our process that's going to show up in our answer. And the rest, arc sine of u over a. My u value is x cubed. My a is 1. Now I'm just going to get rid of that 1. You can leave this as your final answer. That's fine. Just want to drop that 1. Okay, any questions with 4? All right, let's look at number 5. I'll copy this over here as well. Integral of -4 over x squared minus 6x plus 14. I see numerator denominator. First thing I'm going to look at is my denominator, see how many terms there are. There's more than 1. I know expansion is out. Second option, use substitution. But if we let the u value be the denominator, our derivative is going to produce an x to the first power, and that's not going to be a good matching with the numerator. So the degrees are too far apart. Okay. And because the denominator is greater than the numerator, I know I can't do long division or synthetic division. Our last option is arc trig. And it fulfills that condition because the degree in the denominator is more than the numerator by 2 or more, right? Degree 2 versus degree 0. It does have that separation of 2 degrees or more. So we know arc trig may be a good fit. And if we're trying to match with one of these 3 rules, it'll have to be what? Okay. But also, how do we know that it's not arcsecant? Yeah, so I see no square root. So if I don't see a square root, I know if it's arc trig, it's got to be that arctangent. Okay. Okay. And like Jesse said, we're sitting at standard form, which is not quite suitable for us to pull that u value. That u value is not ready to be pulled. So we need to get this standard form into vertex form, and the way we do that, we learned this on Friday, which is completing the square. Okay. So we're going to treat this like a separate problem here. Really, we're going to keep the signs of all these terms. We just need to put a plus space and minus space on either side of that 14. Okay, so just make sure that you don't change the sign of that 14. It'll still stay as that, whatever that sign is. But whatever number we decide to add to cause this to factor, we need to make sure we subtract it immediately so that we don't change the overall value of my trinomial. Okay. Now, what goes inside these spaces? Yeah, b over 2 squared. Okay. Our b value is -6. -3 squared is 9. One is positive, and the other is always going to be negative. The first one is always positive, and the second one is always a negative. And that negative is taken care of with that minus space. Okay. So this should factor nicely. Multiplies to be 9, adds up to be -6. -3 and -3, right? Merge those together. That's just x minus 3 quantity squared. And then we also know 14 minus 9 will just become 5. All right. Let's reset because we now have a form that is more suitable for our problem. Right. But if I want to match with my arctangent rule, same issue with the denominator, right? We got to get those parentheses to show up, 2 sets of parentheses in the denominator, so that we can ensure that we're not pulling the incorrect a and u value. Okay, so I'm going to rewrite that denominator there. Oops, yeah, well, the first one's already, we know it's going to be x minus 3 squared. What about the second one, though? Good. So we want to adapt this form so that whatever we place in here, the result is going to be the same thing as 5. So root 5 squared is the same thing as 5. Now, through this process, your a and your u value may be flip-flopped, but it's okay because they're being added. So it's okay if you have u squared plus a squared versus a squared plus u squared, as long as you know what's the a and what's the u value, right? Your a value is going to be the numeric. Your u value is going to have a variable in it. Okay, so I'm going to identify my a and u value, find the derivative, get this in terms of a and u, and see if I can match it up with my arctangent rule. Okay, make my substitution. I can push the -4 out in front. I know that's the coefficient that's I can put up there. dx becomes du. And then x minus 3, that's my u squared. And once I get past this, once I get past that -4, I've got a perfect match, right? And now I can jump into my integral rule. Keep the -4. 1 over a, my a value is root 5. Okay, arctangent. U over a, there's my u and a value. Plus c. Do a little bit of cleanup here. I can make this as one fraction. All right, any questions? Just want to make sure that we got in some practice with the arc-trig integral since it's fairly new. We only just learned it Friday. All right, anybody still need to look at this? Okay. We're also going to do number 6 and 7. I'm going to change this slightly from the worksheet though. So here's number 6. Okay, so 9 raised to the cosecant 2x times cosecant 2x cotangent 2x dx. So I'm changing it slightly from the handout or from the worksheet. So if I'm looking at this, I'm saying to myself, this is too much for one rule to handle, which means this has got to be a U substitution problem, right? But before we can identify the U value, we want to kind of have an end goal in mind, right? What rule is this going to match best with? Yeah, that A to the U. That 9 is a base A to the U, and we're hoping that this U value derivative will handle this portion here, right? So that A to the U is going to be our best fit. Okay, if you're looking at the trig rules, none of the trig rules will allow us to handle this 9 that's sticking out, right? That 9 is not a coefficient. That 9 is a part of an exponential function. So yeah, our best fit is going to be that A to the U rule. Okay, let me write that rule here. So if we have the target in mind, we have a much better idea what our U value is going to be, right? We want U value to be the entire exponent. Okay. And as a reminder, this is also on your formula sheet here. The derivative of cosecant of U is negative cosecant U cotangent U times U prime. So we have a rule here, which is going to use it to create our derivative. So negative cosecant 2x cotangent 2x times U prime, so times 2. Cross multiply, solve for dx. Make my substitutions. Replace dx with du. All right, what goes away?
Cosecant 2x tangent 2x.
Leftover of
-1.
yeah. So keeping track of those things, right? Negative 1/2 comes out in front. Oh, something that I saw on the quiz as well. Sometimes I see students wanting to merge coefficient with the base, but this base is part of an exponential function. So we're not able to multiply. If this is like another number, we can't multiply those two numbers together. Okay, so those have to stay separate. Okay, order of operation prevents us from merging those two together. So now we can jump into our rule here. Keep the negative 1/2. Okay. And then 1 over natural log of a, my a is 9. And then the rest of the rule, a to the u plus c. My a is 9. And finally, I can put all this under one fraction if I wanted to, or coefficient rather. And then 9 to the u, my u value is cosecant 2x plus c. Okay, any questions with 6? Anybody still need to look at 6? Okay, I'm also changing number 7 a little as well. So this is something that I want to point out because I saw these mistakes on the quiz. So let's talk about that. So I'm changing this slightly from the review sheet. Now, first thing I want to point out is that the issue that I think a lot of students had were students saw these terms and they thought that they had to find a way to merge them together. They thought that these were connected. So because we see a minus sign, there's no division between the terms. There's no multiplication between the terms. There's no parentheses that's connecting these two terms together. We can literally treat this like these as two separate problems. And each have their own rules. So we just literally use substitution for both these terms separately, find the antiderivative, and we just merge them together and then do a plus c once at the end. Okay. But I think what I saw a lot of students on the quiz do where they're trying to convert this to be in terms of something that are a shared trig function or finding a common u value or finding a common denominator. Right, there's no need for that, right? There's no need that these have to even be. They just have to be happen to be next to each other, but they don't have to be connected in terms of the rules we apply. So if you want, you can literally make these two separate integral problems, each with their own rule, each with their own u value, and go from there. Okay. So x over 2 is really 1/2 x, right? Now there's a bit of a shortcut that I want to talk about that will allow us to jump directly from here to here without having to write all the intermediate u substitution steps. Okay. I still want to show all the steps for students who still want to go through that process, and they just if you want to have something that's familiar every time, that's great. But I do want to offer the opportunity to do where we can do a shortcut. We can jump from here to here without having to write all these additional steps in between. And the shortcut is really understanding what's going to come out of that 1/2 x. What's the leftover term? Do you guys know that's going to come out of that 1/2 x?
Just one.
It has to do with the derivative. Okay. Normally, if we were doing chain rule, we would do times u prime, right? So what's the derivative of 1/2 x? But this is not derivative, right? This is the antiderivative. So we got to do something with that 1/2. That 1/2 becomes a what? We got to do the reciprocal. So it's going to be a 2. So if you understand that process, you can skip that whole thing of u substitution Now you only want to do this for cleaner, simpler linear terms, but if you understand there's a coefficient of 2, you can look at the integral rule and say, well, that must be 2 natural log secant of x over 2 plus tangent of x over 2. And that saves you a few minutes of having to write all that in between. So let's practice with this one here. Can I jump from here to here without having to go through all those intermediate steps? What's going to be produced out of that 3x? Yeah, that's it. So negative 1/3 natural log cosine of absolute value of cosine of 3x plus c. All right, so if we know what comes of that, then we can skip all the intermediate steps. All right. But I also want to kind of show those steps for anyone who just wants to go through that full process. So u is x over 2, which is 1/2 x. du dx is 1/2. Cross multiply, dx equals 2 du. Make my substitution here. I get secant of u times 2 du, and that 2 comes out in front, so we see where that 1/2, the x over 2 turned into, right? Turns into that 2. Okay, so we'll hold off on that. We'll come back to it. Go to the tangent side. U is 3x. Okay, we make our substitution. Integral of tangent of u. Okay, that 3 is going to come out as 1/3. So you see that 1/2 x is going to just turn itself into a 2. That 3x is going to turn itself into a 1/3. And we could potentially skip all that and jump directly to the integral if you wanted to. So now we have our rule here in front of us. 2 secant becomes natural log absolute value. Replace the u back in terms of x. Now, there's a negative in front of the second integral, but there's also a negative in front of my rule. So we have 2 negatives that we got to resolve here. Okay, so I'm just going to resolve those 2 negatives there. Okay, any questions there? Okay. All right, let's do, let me skip over to, it's not on this, on these review sheets here, but this is on the from previous worksheet where we're matching slow fields with differential equations. But if you don't have it in front of you, just kind of follow along and we'll just practice listing out properties that we can see in front of us and matching or removing the incorrect choices. So this is number 5 off of the slope fields review worksheets. Okay, so I rewrote the choices, makes it it's kind of hard to see. Okay, so the thing is that what makes the slope field difficult to match is the fact that we don't know what these exact slopes are, especially for these positive and negative slopes. We know what category that it falls under, but we don't know the exact slope value. But what we can do is we can list out some basic things that we're able to see, right? We can see where the slope zeros are. We can see where the slope undefineds are. We know where the positive slopes look like. We know what negative slopes look like. And so we're going to see if we can create some general observations and use those observations to help us eliminate the choices that doesn't fit the ones that the observations that we're seeing. Okay, so it may be kind of hard to see. I'll bring this a little bit closer here. Do you see where a slope 0 is going to occur?
Roughly around like x equals 3 or y equals 3.
Yeah, y equals 3. I know that first quadrant, it kind of all looks like slope 0, but if you can kind of see that distinction there, it's only y equals 3 being slope 0, and then these are all slightly gradual slopes. Right, so okay, so y equals 3. Mostly, right? We do see some values that is not quite defined there. Okay, what about slope undefined? Where do you see a collection of slope undefined?
X equals 3.
Yeah, there's whole whole -3, right? Whole blank space right here along that vertical line. Okay. All right. Do you see a collection of positive slopes? Can you make some general observations as to where positive slopes are going to occur? Yeah, anything above y equals 3, right? Those are all, I mean, different variations, but these are very slight positive slopes, but these are still positive slopes. Okay, so above y equals 3. Okay, where do you see negative slopes?
Below y.
Yeah, below y equals 3. Okay, so we made some good observations. We should be able to eliminate, multiple incorrect answers. I think an easy one to target is this one here, slope undefined. That means that if I replace x with -3, it should cause my slope field to just be completely undefined. But which ones are not undefined, which we can just take out?
C and A.
Yeah, so let's try A here. If I plug -3 in for x, I should get 0 undefined, but there's no denominator at all, so there's no chance that this could ever be undefined. And we know that's inconsistent with what we've observed here. And then for C, if I replace -3 in for x, I'll get 0 in the numerator over y minus 3, and y doesn't have to be 0. So we know that we can't guarantee a slope undefined when x equals -3, so we can eliminate this choice. Now for B and D, this works, right? -3 in for x, I get 0 in the denominator. -3 in for x, I get 0 in the denominator. So these two still stand. But I think there's one that I can eliminate just by looking at what I know about positive and negative slopes.
D.
Okay. What about D?
B is square, so anything would be positive.
Yeah, I'm looking at that as well, going, well, both are square. There's no chance of this ever being negative. Right? If there's no chance of this being negative, that means there's no negative slope that's going to come out of it, which is inconsistent with what we see here. So I'm looking at B going, all right, this is always positive, so this should be an incorrect choice. I still want to test out D, but at least I'm pretty certain just by eliminating that A through C are not good fits. But let's look at each of these options here. If I put 3 in for Y, I should get 0 overall. 3 minus 3, that's 0. That works. If I put -3 in for X, I get 0 in the denominator. That works. Notice that my denominator is squared, but my numerator is not, which means that the denominator has no chance of being negative. Only the numerator. The numerator is dictating whether the slope is positive or negative. And when Y is greater than 3, that's going to ensure this overall fraction must be positive, which we see to be true. But if our Y value dips below 3, then all of a sudden my numerator is going to become negative. That's going to force this fraction to be negative, and that's consistent with what we see here with negative slope. Okay. Okay. All right, let's do one more here, number 6. Let me write those options here. Okay, so slope 0. All right, do we see slope zeros?
Along the y-axis.
Okay, so here's the thing is, we're not entirely sure, right? Sometimes the axis, if it's occurring along the axis, sometimes it's either hidden from view or we can't tell the tick marks from the slope zeros. So if we see slope 0 or slope undefined, or what we think is slope 0 or slope undefined along the axis, and those are the only places that we see them, I'll put a question mark around them because I don't want to rely on that information because it's little too, it's not defined as well as we would like. So let's observe the other things first, especially when we don't see any slope undefined or slope zeros where we can clearly see them, right? If it's along the x and y axis, we got to be careful. It's not, sometimes it's not displaying what we would like to see. Okay, what about positive slopes?
Quadrant 1
Mm-hmm.
and quadrant 3.
Mm-hmm. Okay, how about negative slopes?
2 and 4.
Okay, so we may have to make some more detailed observations about positive and negative slopes, but this is a good place to start. We should eliminate some wrong choices here. Let me put some order pairs here, right? How about 1, 1, negative 1, 1. So I can use those test points to kind of help me eliminate, right? Do you see any that we can just outright remove?
B and B.
Okay, why B?
Because it will come out to be a negative at 1, 1.
Yeah, so 1, 1 has to give me positive, right? And if I put 1, 1 in, I'm getting negative. So I like going through this method of just eliminating the wrong choices. Those are quick and easy rather than finding the right one at the beginning. Okay, and then D, yep, you're right. If I put 1, 1 in, I'm getting negative. So that's a clear way that I know it's wrong. Okay, so that's good. I'm down to 2 choices. But looks like if I test out each of those ordered pairs for quadrant 1, 3, 2, and 4, I'm not getting any distinction. Okay, is there anything else that could help us distinguish?
You can test out a point in quadrant 3 and see if it comes out to be positive.
Quadrant 3. Well, quadrant 3, both will give me positive, right? So here's the thing. I want to point something out here. I want to point this out. Okay. What happens to create that slope of 1?
It just has to be the same number over the other.
Yeah, so this is kind of divisional thing, right? 1 over 1, 2 over 2, 3 over 3. Meanwhile, we know that C is not going to quite work out because if it's truly x times y, it should be 1 times 1, 2 times 2, 3 times 3. These should all become a lot steeper, right? And we see that's not the case. So if I see something like this, where I see like a pattern of a slope, it looks like 1, but at least we know it's all the same. So it's all being created the same slope at these order pairs that are matching. So yeah, that's going to help me realize that it's going to be this x over y. So sometimes we have to kind of dig a little deeper, look at some more behavior, some consistent behavior that we see across order pairs. Okay, so we didn't get a chance to get into worksheet 2, but tomorrow we'll kind of jump around between the different test topics, but we've kind of seen most everything that I wanted you guys to be able to do between these 2 days, and then tomorrow we'll kind of just hit those maybe specific topics or kind of do one of each. This afternoon I have a help session going over more solving differential equations. They'll be recorded. I had one this morning as well. And then tomorrow morning and afternoon, I'll go over more use substitution, more similar to your quiz 5 problems, and maybe even some slope fields as well. Okay. And then Thursday is your test. I encourage you guys to work through some of these additional review worksheets that I have on my website. I have worksheet 2, worksheet 3. I just put up worksheet 4, which I'm going to do Thursday morning for the review session. But if you have time, I encourage you guys to work through them at your own time, right? That way you can kind of just, if you have specific questions about problems, you can reach out to me or get that resolved rather than waiting for Thursday morning. But Thursday morning, I will go through worksheet 4 at 7:15, going through the entire review sheet. So, all right, thanks everyone. Hope you guys have a great day. See you guys tomorrow.